All right, so let's get started. Welcome back, everyone. This is going to be the second part of the reinforcement learning module. Today, the audience is pretty sparse, so feel free to ask questions and interact more. We're going to go through a bunch of the material that is basically core reinforcement learning algorithms. We'll skip some of the details and try to connect it back to the objectives that we derived in the last lecture. But before we go into the actual content, I'd like to talk about some logistics. So we're approaching the end of the semester, and there is a couple of homeworks left. So homework 3 is due tonight, and homework 4 will be out next week. So homework 4 will be much easier, or I would say relatively easier than the previous homeworks, just to give you guys more time to work on the project. Because, well, the second announcement is that the project presentations are approaching. So initially, we planned it to be May 1st. Due to some scheduling reasons, we had to move it to April 30th. And this year, we're going to be organizing, instead of standard presentations, we're going to have a poster session because we have more than 30 projects. So just giving everyone 10 minutes to talk might be too much. And it's going to be a full day of talks. Everyone will get tired. But poster session will be more interactive. You'll get feedback from your peers. You'll get feedback from us. Of course, we'll, to some extent, we'll grade your presentations, and your posters will be worth 20% of the project grade. So we'll update that information on the website, the posters and the percentage. But there is only 3 weeks left, so I would encourage you to focus on trying to sort of make as much progress on projects as possible at this point. The good news is that the final report will be a bit later, so you don't have to prepare your poster and then submit the final report right away. You'll have some time afterwards to incorporate either the feedback from us, the feedback and comments from your peers, as well as maybe finish some of the experiments and get final results. So what we expect from the posters, since there is not much time left. So in terms of the expectations for the content that we want you to present in your posters, is that first of all, the motivation of the project should be super clear and final. The method should be clear and final, and basically the goal is to present your method or your experiments, your study. And we still think that results can be preliminary, because you'll have time to finish the results and to get the final results in the week after the poster presentations. So it's great if you have final results. It's OK if some pieces and parts are missing. So don't stress too much about that. It's fine. And well, the final report will be due May 10th, which you'll have a bit more than a week afterwards. So any questions about the logistics part? No questions. Yeah, if you have any questions about your projects or you need some feedback in the meantime, feel free to stop by the TA office hours. Every group has their TA, so just discuss with them. OK, so now let's go directly into the lecture today. So the focus will be, so we've covered some intro to RL and control as inference framework during the last lecture. And today we're going to go a bit more into the algorithms. So we're going to recap, and most of the time we're going to spend actually on looking into policy gradients and Q-learning, the basic algorithms and reinforcement learning. And at the very end of the lecture, we'll just connect it back to the max entropy framework, and we'll see how Q-learning and policy gradients connect to each other. Yeah, so that's the plan for today. So remember that we introduced the Markov decision process in the last lecture. And basically, we have some sort of environment that provides us rewards and updates the states. Given the state and reward, agent somehow decides which action to take and submits it to the environment. And we iterate in this loop. probabilistically speaking, we have some distribution over the initial state, some transition function that describes the dynamics of the environment, and we have a policy, which could be deterministic or probabilistic. So the part that was hard to incorporate in the graphical model was this reward, which is a function of our random variables. In order to incorporate that, we introduced the auxiliary variables right here, which are binary random variables indicating the optimality of the action taken at a given time step. And we assume that, well, this probability is somewhat arbitrarily set to x of the reward, right? There's a way to derive that actually from the max entropy principle, from the basic principle. So you can look up this in the Brian Zeber's thesis. But for now, we just set it to this formulation. So in the standard RL, we looked at two functions, right? At the value function of the state, which is the expected discounted rewards that we're going to get into the future if we are in the state S and we keep acting according to the policy pi. And then we looked at the Q function, which is the function of state and action that basically answers the same question, but just conditions also on the first action that you take. Then we realized that the optimal value functions and the optimal V functions at every state are sort of connections through this recurrence that can be computed. Given the optimal, let's say, value function at the leaves, we can compute the optimal values at the root nodes by just running a dynamic programming type of algorithm on the tree, right? And then finally, if we want to get the optimal policy, we can say, in case of MDP, we can get it by just greedily selecting the actions with respect to the optimal Q star function, right? So after we switched to this probabilistic framework with auxiliary variables, we asked the first question we asked was, what can we do with this graphical model, right? And the answer was, well, if we have a reward and we have some sort of action prior and some sort of transition dynamics, we can actually run an inference query on it. So we can query the model and ask what is, let's say, the distribution over the trajectories given that we acted optimally, or we want to act optimally. And what this distribution was equal to was actually the probability of the initial state, right, and then the product over the dynamics, right? So it was ST plus 1 given ST AT. And then we multiply this whole thing with the exp of the rewards at every time step. And we sum over the time steps. And this is proportional, right? Because it's a conditional distribution, it's proportional to the joint distribution. Next, we try to derive the forward-backward algorithm in this Markov chain-like model. And we derived expressions for two messages, where one of them was actually, so this beta message corresponded to the probability of being optimal at time steps t to capital T, given that we were in the state ST and we acted as AT, right? So it was pretty, the intuition behind it is that this beta message assigns probability, or basically gives us the probability of being optimal if we take an action AT from the state ST, right? Which is pretty similar to the intuition of the optimal Q function. The optimal Q function tells us what will be the value that we will get if we keep acting optimally, and we select action AT from the state ST, right? So that's why we actually decided to name it, sort of logs of these messages as Q and V. The other thing that we noticed is that the V message, VST, was basically a soft max, right? So this is a soft max over the actions. of the optimal Q, soft Q function, right? Which turned out to be pretty similar to the standard RL, where V, the optimal V can be computed through the max through the recurrence that I just showed in the previous slide. And finally, we derived the probability of the action, given that basically the entire trajectory is optimal, right? So this is the inference-based optimal policy that we derived from the graphical model. And how would we compute this policy? Well, one way is if we know the dynamics, the transition dynamics, we can just start from ST. We can compute the forward pass and then the backward messages, and then compute the Q and V at this given time step. And this would be equivalent to some sort of planning in the graphical model. Okay. Then we ask the question, well, this policy, this inference-based policy that we derived from the graphical model, does it optimize some sort of objective or does it not? And as it turned out, it optimizes this Kullback-Leibniz divergence between the probability over trajectories induced by the policy and the probability of optimal trajectories, right? So this is our probability over tau given O and T. And after a little bit of math, we realized that, well, what it's equal to, it's actually equal to the expected rewards, right, plus the entropy term, which has an interesting meaning, which says basically, I would like to find a policy that maximizes the reward while acting as random as possible. A little aside, in case of the deterministic dynamics, we can get this objective directly by optimizing this by writing out this Kullback-Leibniz divergence. In case of stochastic dynamics, we ran into this issue with optimistic behavior of the agent, or I would say like opportunistic behavior of the agent that was induced from the graph. So we had to fix it by introducing some variational distribution that sort of prevents the agent of attempting to exploit the dynamics, right? By optimizing the elbow, we can see that we get pretty much the same objective. Okay, so any questions about the quick recap so far? No questions. Cool. So now we're going to go into actually trying to figure out how we learn these policies by optimizing these objectives. So in reinforcement learning, there's a class of methods called policy gradients. And basically what we're trying to do, we're trying to directly optimize the parameters of the policy, so represent the policy in a parametric way. And we're just looking at this objective function and trying to find the parameters that would lead to the maximum possible expected returns, right? So how we go about optimizing this objective? Well, we can first start with the initial policy. We can generate a bunch of samples. Then we can fit some sort of a model, and in the simplest case, we can just estimate the return from the trajectories. And then we're going to go and improve the policy a little bit. And it could be a gradient step improvement. That's why it's called policy gradients. And after that, we can go and come back to the first stage and collect samples again under the new policy. Again, estimate the returns, improve the policy, and iterate in this cycle. So here's just a quick example of how this might look like, in some sort of simulator. Right. So here we have an agent that tries to control this humanoid robot in a simulated environment. So the physics is simulated. Every single action basically sends certain torques to the joints and exerts forces so that the robot can move. And then what we're trying to do, we're trying to learn a policy that would observe the state of the robot and try to, execute some sort of behavior over time. And let's say the robot is rewarded for for running fast in one of the directions. And in this case, we want the robot to run in the right direction. So you can see that from iteration to iteration, the policy initially starts with very bad behavior, and then eventually it slowly converges to some sort of nice behavior. And after a lot of iterations, we can actually even further optimize the behavior. All right. So yeah, so the video is taken from this paper at the bottom of the slide by John Schulman. So this is a variation of the policy gradient or direct policy optimization algorithm. Of course, as you can see, the number of iterations is pretty small here. And there are additional tricks that you need to take into account in order to be to design an efficient algorithm. But let's step back a little bit and let's think just how can we optimize this stochastic objective in general. And one way that I just described is policy gradients, where you directly optimize the objective with respect to policy parameters. The other way would be to estimate the value functions, maybe the v function and the q function of the optimal policy, and not actually represent the policy explicitly. So the point here is that if we have the optimal q function, remember that we can derive the optimal policy from the optimal q function in the MDP by just acting greedily with respect to the q function. So in this case, these methods are target to do that. So there are so-called actor-critic methods that combine, in a sense, the value function estimation and the policy optimization. And the idea is that you start with some policy, but you also concurrently estimate, and you try to optimize the policy, but you concurrently estimate the value functions and use it to improve the policy. Right. So finally, there are model-based methods. And the point here is that I mentioned that we may not know the dynamics of the environment. If we know the dynamics of the environment, we can actually use that dynamics to try to do some sort of search. If we don't know the dynamics, maybe we could try to learn the model of the dynamics, right? And then use this model of the dynamics for planning. And at a high level, planning is done as follows. So let's say you have the model of the dynamics. We have some sort of we can take actions according to some policy. We can actually unroll our dynamics model up to some horizon into the future, and then try to optimize the sequence of actions that we're taking directly with respect to, optimize the encountered rewards with respect to the sequence of actions directly. So the model allows us to do that. But we're not going to go into this in this lecture. Maybe like a little connection is to our graphical model. So when we compute this forward and backward messages, this is equivalent, in some sense, to a model-based method. So another alternative is to use this model to improve the policy, right? And this is what, for example, AlphaGo is doing. You can use MCTS distillation and eventually not only use model-based planning and then have some sort of implicit policy that depends on the model, because maybe executing and looking ahead within the model is a bit expensive in terms of computation. So in that case, you would want to distill this procedure of planning into some sort of policy that can imitate your planning. We're going to focus actually on the first two, and we're going to focus actually on the very basic reinforced algorithm for the policy gradients and Q learning or fitted Q function iteration for the second one. So let's try to derive policy gradients. Again, we're going to start with this. Well, I should ask the question first. Any questions at this point about this rough categorization? No? OK, so then let's derive the policy gradients, right? We will start with our objective function. And we'll call it j theta, right? So how do we compute this expectation? Well, if we have access to a simulator or an environment, and we have access to our policy, we can just sample these trajectories. And how we sample these trajectories, basically, let's say we start with state 1, and we say environment.init. And then after that, we're going to loop over the time steps. And every time step, we're going to first produce an action, which is sampled from the policy. Okay? And then after that, we're going to submit this action to the environment. So we're going to say, get me st plus 1 and reward at time point t, and let the environment actually return me this. Right? So this is some quick pseudocode of how you would be executing a policy in an environment and collecting these trajectories. So this procedure sometimes is called rollout. You plug in the policy and you roll out trajectories from the environment. Now, if we would like to optimize the parameters of the policy, we can compute the gradient of this objective. And to compute the gradient, you can see that these guys don't explicitly depend on our policy parameters, right? So the dependence is hidden in the samples. So to actually compute the gradient, let's try to differentiate the expectation itself. And then, because integration is linear, we can push the differentiation operator through and compute actually the gradient of the policy itself right here. Now, we can do this so-called log derivative trick or square function trick. And how this works, so let's derive it right here. It's pretty simple. So this is our gradient of the probability of tau. Let's divide and multiply by the probability of the trajectories, right? And look at this part, right? So this part is basically equal to, and you can verify that this is gradient of the log of the probability of theta of tau, right? So that's exactly what we got here. All right. So the good thing is that we have again our probability over the trajectories here, and we integrate. We have the integral, so basically this part can be converted into the expectation again. So we convert that into the expectation, and we get expectation again of our returns multiplied by the gradient of the log probability theta of tau, right? So now to estimate the gradient, what we can do, we can just sample these, we can just sample a bunch of trajectories and then compute these values in the brackets here. Just average them over the sample trajectories, and we'll get an unbiased estimator of the gradient. And in general, this construction here in the brackets, it can be generalized to any stochastic computation graph, or in general, any graph of computation where there are some nodes that are stochastic, and there is a way to take the original objective and to rewrite it into so-called surrogate objective, so that the gradient of the surrogate objective will be an unbiased estimator for the gradient of the original objective. Okay, so if you're interested in that, you can take a look at John Schulman's paper on gradient estimation using stochastic computation graphs. And recently, there was another paper that tries to provide an infinitely differentiable objective of this sort, where not only the first gradient would be unbiased, but any order of the derivative of any order will be sort of an unbiased estimator of the gradient of the original objective. Sorry, of the derivative of the original objective. All right, now let's take a look at this term a little bit more in depth. Right, so this is the gradient of the log of the probability over the entire trajectory. And the probability of the entire trajectory is our probability of S1, product, probability of the transitions, right? And then basically multiplied by the policy, right? So these two guys do not depend on the parameters. So once we hit them with the gradient, they will just disappear. So what we arrive at is basically expectation of the two terms. So one term is just the sum over the gradients of the log probabilities of the actions under the current policy, right? So we rolled out the trajectory. For every single action in the trajectory, we can compute the probability of taking this action under the current policy, right? And then this thing is weighted. It's basically weighted by this sum of the rewards term, right? So if the trajectory was good, the weight will be high and positive. If the trajectory was really bad, maybe the weight was going to be negative. So it's basically weighting. So to explain it a bit more visually, so imagine we sampled a bunch of trajectories. Now, some of them are really bad, and some of them are going to be really good. So what this will result into, for the trajectories that are really good, we'll try to, the gradients will be positive, basically positively weighted. So we'll try to push the parameters of the policy so that these good trajectories under this policy are more likely. And then for the trajectories that are negative, right, we'll try to push them in the other direction so that these trajectories under this policy are less likely. Any questions? Does that make sense? Okay, so apparently there is a relationship between this and the maximum likelihood. So imagine that instead of sampling from our policy, we had a policy that we would like to optimize to imitate some expert. So expert gives us trajectories. What we can do, we can actually write down the maximum likelihood estimator for this. And it's given on the slide down there. So we roll out taus from the expert. And in this case, we don't have a reward. We're just trying to maximize the log likelihood of the actions that we're taking on these specific trajectories. But what this actually is equal to, we can actually add a reward here, where the reward function or basically virtually add a reward, where the reward function, and I'll call it like reward expert, will be giving always ones for the trajectories that are the expert trajectories, and for all other possible trajectories it will give zeros, right? So it's in a sense equivalent, but note that our original objective that is used for policy gradients is slightly different. So we don't have the expert, therefore we're using reward as a proxy, right? Or as a signal that allows us to reweight. So you can think of this as sort of importance reweighted, or similar to importance reweighted maximum likelihood. The difference is that the importance weight could be negative, it could be positive, and this objective is a little bit sensitive, or I would say like pretty sensitive to the shifts in the rewards. So imagine if you added a constant to this reward, maybe all your negative rewards are no longer negative, so that would affect actually how the weights will be placed on all the samples. Okay, but these are details. So let's see how we build an algorithm out of this, right? So we had our expected gradients. We can approximate them by sampling a bunch of trajectories and then computing these two terms, right, under the current policy. Know that we have to sample from the same policy which we're optimizing. Therefore, it's called an on-policy reinforcement learning algorithm, because if you sample trajectories under a different policy and then you try to optimize your current policy, this will no longer be a correct estimator of the gradient of the objective. So again, we iterate between generating samples, estimating the returns, and improving the policy. And the simplest possible algorithm here would be called reinforce, right, which does pretty much this. In the first step, we collect the trajectories. In the second step, we compute the surrogate loss function that adds these like log probability terms. And then the final step, we just make a step on the parameters, right? Okay. So quick summary in the policy gradient parts. So we've derived this reinforced algorithm, which is pretty much the simplest policy gradient algorithm. We can represent the policy with any parametric function. It could be a linear function or a neural network. We just plug it in, compute the objective, and just run our optimization routine. The only thing that we need that is different, let's say, from supervised learning, is the part for generating samples. Right? You take a policy and then you throw it into your environment and you generate a bunch of trajectories. That's not what we do usually. And supervised learning, we're already given a data set that we're trying to use for optimization. So there is a relationship between policy gradients and the maximum likelihood objective. I can think of rewards as some sort of weights that are reweighting our log odds of the actions. And finally, like a quick note that this basic reinforced algorithm is extremely high variance. One of the problems here is that you're trying to score basically the entire trajectory of your actions with all the rewards that you obtain for this trajectory. But let's say an action at step 5 does not affect any action, any rewards for the previous actions. And that's how the MDP works, right? If you take an action 5, it wouldn't affect rewards at step 4, 3, 2, and 1. So a better way would be to rewrite actually this objective and to take into account this action causality, as well as try to reduce the variance of this estimator using some value function estimators. So there is a way to estimate the values, or have a value function estimator that you can be fitting along the way, and then plug it into the objective function. So this is what actor-critic algorithms are trying to accomplish. We will not look into this in the lecture, just for the interest of time and also not to distract from the PGM part. But you're welcome to look up chapter 13 from Sutton's and Barto's book, as well as check out policy gradient lecture in any deep reinforcement learning course. There's one that we have here at CMU, actually. All right, any questions so far? Nope. Okay, so before we move on, so remember that slide that we had with different approaches to reinforcement learning, how we can optimize this stochastic objective. One of them that we covered was direct policy optimization. Now we're going to look into how we can actually, get rid of the dependence on the policy. So the algorithm was on policy, and as I mentioned, if you sample these, let's say these actions, right? So these n trajectories under a different policy, then the estimator would be incorrect, and therefore we won't be able to optimize the parameters of the policy we're interested in. So is there a way to somehow, circumvent this, and maybe we could actually work with the value functions directly and then induce the optimal policy from the optimal value function after we learn it? So there is a way to do that. Maybe one observation that we can make, and we've already made it before, is that if we have the optimal Q function, we can easily get the optimal policy out of it, optimal deterministic or greedy policy. But also, if we don't have the optimal Q value, the Q star thing, let's say we have some policy, and we can compute the corresponding Q pi for this policy. And let's say we're able to execute this dynamic programming. Let's say start from one state and then go and estimate the Q for this pi entirely for all the states and for all the actions. So if I select action AT according to this argmax, I can get some sort of policy pi prime, right? So can anyone say how pi prime relates to pi? Is it identical? Is it better? Is it worse? Right, so I guess the answer here is that because we have this q pi that we computed exactly, and then because we're acting as argmax, meaning that at every step we're going to select an action that is at least as good as if we were following the policy pi, right? So it means that we're going to be at least as good as our original policy pi. So this suggests, again, a way to improve our policy together with the Q function now, right? Initially, we'll generate some samples from some policy. Then we can try to fit this Q pi SA, or basically estimate or compute it entirely. And then we're going to substitute the policy pi with our pi prime. Okay? And this will be the policy improvement step. So this algorithm is called policy iteration. And then I guess the hard part here is how to compute this Q pi SA, right? And in this simple tabular setting, we should be able to do that with dynamic programming, right? We're going to start from some state and then recurse. And every time we take an action, we're going to just look at all possible actions and then weight them according to our policy, right? So that's how we're going to evaluate the Q pi. So Q pi is basically the reward for taking an action A from state S plus the discount factor multiplied by the expectation with respect to the transition. And then we have this V pi. Assuming that we can compute V pi and assuming that we can expand from the current state in all possible other states under the action A, right? If we have access basically to this transition function, we can compute Q pi SA, right? And then once we compute Q pi SA, we can update the policy, right? So how do we compute now this V? Well, the V will be computed through the recurrence. So we'll start from some state S. We act according to the policy pi. And then we're going to transition according to the transition probabilities, right? So the idea is that we start with some policy pi. We can evaluate the policy and get this V pi for every single state. Again, we're in a tabular setting. Everything is tractable and determinate, and yeah, everything is tractable, and we can enumerate all the states and actions. Then we go back and compute the Q pi, and then after we computed Q pi, basically answers basically we finish the first step, and then we can compute the pi prime as the argmax operator. Okay, so how does it look like intuitively? So let's say we start with some initial policy pi and some initial value function. So on this side, right, this line corresponds to the value function landscape that corresponds to specific policies, right? So these are value functions for the policies. And on this side, we have policies that correspond, greedy policies that correspond to specific value functions. So what we do, basically, starting from some initial policy and value function, we first compute the precise value function for that policy. Then we go and improve the policy. We say, hey, let's set the policy to be greedy with respect to this value function. Then we're going to recompute the value function again, now with respect to the new pi prime, and then keep iterating. And then eventually the hope is that by iterating between the evaluation of the policy and the improvement of the policy, given the V function, the hope is that we're going to converge to some stationary point, where at some point the policy pi star will evaluate to V star, and improvement or greediness with respect to V star will bring us back to pi star. So we'll be basically at this stationary point. Any questions so far? So I guess I didn't answer the question, how do we get rid of the policy? Because in this policy iteration algorithm, we're still sort of attached to the policy, but we introduce this value function that helps us to sort of update the policy, not with the gradient step, but maybe with this recomputation step, right? When we go from pi to pi prime. And policy becomes like represented sort of implicitly, right? Because pi greedy with respect to our value function is the argmax, is represented through the argmax operator. The question is like, can we still get rid of the policy? And the answer is yes. So instead of doing the argmax within the policy, why don't we just iterate between, the QSA directly and the VS? And we know that, once we get to the optimal policy and the optimal value functions, this relationship should hold. So this relationship should hold for the V star and the Q star. Okay? So in a sense, policy will be derived from the Q function through the argmax. And then in the value iteration algorithm, we don't actually need to represent the policy itself. We do need to get the data from somewhere, right? We do need to get, these S's and A's, but, in the tabular setting, which is can go and enumerate all of them, right? So we're going to go through all the states and through all the actions. We'll compute this this Q for all the states and all the actions, and then recompute again the V function also for all the states again, and keep iterating between the two steps. So this is all good, but we will not be able to do that in very high dimensional spaces. So let's say our state space is very high dimensional. And so what do we do in this case? Let's say our states are some sort of images like we have here. And in this case, we can just we can execute the dynamic programming, and we cannot basically compute VQSA for every single state in action, right? So, but what we can do, we can represent Q as a parametric function of the state in the action, right? And then try to slightly change the algorithm, right? Now, instead of trying to enumerate all the states and actions and execute this dynamic programming procedure, assuming that we can get trajectories or basically pairs of states and actions from somewhere, and starting from some initial value function, right? We can compute these y's or the targets for the Q function. So at the first step, we're going to compute rewards and this term, which is approximately equal to the max over A, Q phi S prime A, right? So we have this expectation with respect to the transition function, right, of the value function at the next step, at the next state. Given that the first state was S, actually this should be Si AI, right? So knowing that the optimal Q and V functions are related through this max operator, right? We can connect them, approximately in this case, and then we can construct this yi's, right? And yi's will be the new targets for the Q function. So in the next step, we're going to update the parameters of the Q function by optimizing this objective, right? So question for you guys. Why do we optimize this objective where we have this yi, but the yi sort of depends on the Q function here? So wouldn't we, get stuck with some initial Q function? Like why does Q function improve in this case? Right, because we're also getting the reward. So the data that we're getting is coming from the environment. So the initial Q function can be completely irrelevant to the specific environment, but because we keep getting the reward, these yi's are better estimates of the value of the Q at this state in action, right? And then by iterating between the two, we'll eventually converge to some Q function. Of course, in the very high dimensional setting, and when the Q function is parametric, we don't have a guaranteed convergence to the true optimum, but we'll converge somewhere. So here's the policy-independent algorithm that we get from here. So let's say we have a data set. We collected a data set under some policy. Now, note that we're saying right now, not under the policy that we keep optimizing, but under some policy. Right? And then there are two steps, where the first step computes the targets for the Q function, and the second step optimizes the Q function with respect to parameters of the Q function. And technically, given a data set, and the data set would look like this. So let's say S prime AR, and then we have some values here. So after we collected the data set, we can execute these steps multiple times, let's say k times, and we'll get, for this specific data set, we'll get a new Q function. And then we can go and rerun and recollect a new data set, and then keep optimizing. The question is, like, what kind of policy, right? It says under some policy. What is the policy we would use in this case to collect the data? And the answer is there could be different policies. Usually people do some sort of epsilon greedy, where you have your Q function, so you can act according to the greedy policy that would try to take the argmax over Q. But instead of being greedy all the time, you can sometimes add a bit of randomness. So you'll either pick a random action with some epsilon probability, or you're going to be acting in a greedy fashion according to Q. So we can use this type of epsilon greedy policy to collect the data. Again, epsilon greedy is sort of suboptimal because the more greedy you are, the less exploring, or in some sense, you're not potentially exploring the environment. You're not able to collect certain experience in certain parts of the environment that would inform your Q function, right? So you may converge somewhere, to a suboptimal point. And there's active research into how actually to make this policy, the exploration, become more efficient in reinforcement learning settings. So if you look at the error function, this is basically trying to take the second line and plug it into the first line, right? If you look at the error function and assume that the error, let's say at some point error becomes equal to 0. So if the error is 0, we can say that we've arrived at the optimal Q function, because the relationship that we get here is the relationship that holds true for the Q star. Right? And then since we are at the optimal Q function, we can say that the greedy policy derived from the optimal Q function will be the optimal policy, or an optimal policy. Okay. Before we move next to the soft policy gradients and Q learning, do you guys have any questions?
I have one question. So I didn't quite understand why we can regard the vanilla Q iteration algorithm as a dynamic programming problem.
Right. So why is this a dynamic programming problem? So let's go back. So in the fitted Q iteration, it's no longer dynamic programming. But when we are in this tabular setting, so I would say, right, when we are estimating the Q, right, or the V in this case, and we have access to our environment. Let's say it's a tabular environment with a grid world, with an agent that is trying to move and get to the goal state and get some reward for that. So you can start from some state, and then you can expand according to all possible actions that you take under your policy. And then from there, you can expand according to the dynamics, assuming that you know the dynamics. And then again, from the next states, you can further expand down. So you will basically go all the way down, and then you will back up. And you can compute the intermediate values for the VS through this recursive relationship.
So it's kind of like the possible transition is exponential.
Yes. Right. Right. Exactly. Exactly. So also how this is related to our max entropy graphical model, if you remember, we would send message. Let's say we have some sort of horizon of t. So to compute the q value at this point, which is the message beta t. So q is equal to log beta tstat, right? So to compute that thing, we would need to go and to sort of do the backward pass, right? So we're going to go forward, and then we do the backward pass from the capital T all the way to the current t. And this will be equal, well, in some sense, sort of equivalent to this, backup from the bottom of the tree all the way up. So this is the relationship between the standard RL and the max entropy RL. But let's now move to the soft policy gradients in Q-learning to see like how these things are related, right? So once again, the only difference, so far, both in Q-learning and the policy gradients, we started from the objective, that was the expected discounted rewards, and then we tried to optimize it. Now, the only thing that this graphical model provides us when we derive this objective function for the inferential policy is that it adds this term, right? It adds this entropy of the policy to the objective function. So the change is pretty minimal, but what happens is that we can say, well, let's try to optimize that objective, right? That was the original thing. Now the new thing is given here. So we just added the policy entropy term to our objective. And we're going to do the same thing, right? We're going to compute the gradient of this thing with respect to theta, right? And we can try to optimize it and find the policy that would basically approximate our inferential policy. So why we want to do that? Why are we not satisfied with the inference? So the policy that we originally had, if you remember, probability of taking an action at state t, and then being always optimal, right, from that point into the future, or maybe being always optimal through the entire trajectory, right, from the first step until the end. So to compute this probability, we'll have to do this, forward-backward procedure. And to do this forward-backward procedure, we need the dynamics, to know the dynamics of the environment. So one way to do is to learn the dynamics and then do inference under that dynamics, which will be equivalent to planning. The other thing is let's just ignore this objective, and knowing that this policy, inferential policy, optimizes this objective that is given on the slide, right? Why don't we just learn the parametric policy that also optimizes this objective by just gradient descent? So I'm just rewriting this a little bit. So I'm combining the two expectations. And we have a sum from t to capital T, and then expectation over the pairs of states and actions. And then we basically have a reward and the negative log probability of the action, right? So basically, like the only difference is that instead of having the standard rewards, which is augmented rewards with the entropy bonus. So we give a bonus to our policy to be more entropic or more sort of random while optimizing the rewards, right? So there is not much change. You're going to take this objective, plug it into your reinforced algorithm, actor-critic, other algorithms. You will get an max entropy version of that. Okay. So, but the interesting thing happens is that there is a nice relationship between this policy gradient and Q-learning. So it turns out that, so what we did before, we derived the policy gradients and then we derived the Q-learning, and there was like this, step-by-step procedure where we eliminated the dependence on the policy, right? So here it's a little bit more straightforward. We'll just try to differentiate this objective with respect to theta, right? And now we'll just expand it and use the log probability trick. And also note that this log pi ATST is actually equal to Q, QST AT minus VST, right? And this is coming from the expression for our optimal policy. If you remember our optimal policy, ATST, right, optimality 1 to t was equal to exp of Q minus V, right? So if we take the log of that, if we take the log of that, we'll get the difference between the two, right? So now we're going to plug in these guys in here. So we'll assume that log pi theta ATST is actually coming from the from the difference between the two, and we'll put parameters theta here and theta there, right? So when moving from this line to that line, so basically what I did, I rearranged slightly the terms here so that the sum goes from 1 to capital T, and then the inner sum will go from T to the capital T, right? So we get rewards from T to the capital T as well as like the log probabilities from T to the capital T. So this expression on the slide is QST plus 1 AT plus 1 is basically using the definition of the log pi, right? Now further, like slightly rearranging the terms and doing some algebra, so basically expanding this guy, that guy, and slightly rearranging the terms, we will get to the expression down there. So basically it's a bunch of trajectories that we sampled, and then the gradient with respect to our Q function that now depends on the parameters theta. And then in the parentheses we have our STAT. So this softmax, so why do we get softmax, right? It comes from the definition of the VST, right? If you remember, this was log integral exp q, right? So this is the thing that we derived in the max entropy RL lecture, last lecture, for the V. So, and this log sum exp is basically the softmax operator here. So what happens is that, so let's try to relate this to the actual Q learning, right? So let's say we have some sort of parametric Q function, and the standard Q learning, we were iterating between, trying to add the reward plus, let's say, discounted max of the Q, and then trying to refit this back to, refit the Q function to match the Y's. Instead of max, now we have the softmax, right? So in the standard Q learning, the update rule for the parameters of the Q function is the initial parameters plus some alpha step multiplied by the gradient of this QSA and this term in the parentheses. And then we recompute the value function as the max over actions over the estimated Q function. Now in the soft Q learning, it's pretty much exactly the same. The objective that we just derived by substituting the policy in the policy gradient with exp of Q minus V gives us exactly the same objective as in the standard Q learning, but max is substituted with a softmax, right? And we can further control how soft or hard this thing is, right? We can add the temperature here. So if you remember, we can technically add this alpha coefficient to the Q function in the exponent. And then the larger the alpha, the higher the temperature, the more sort of random the policy is, the softer the max. And then if alpha goes to 0, basically the temperature goes to 0, it will be pretty much hard max in this case. OK, so this is an illustration of this algorithm applied to to a simple navigation problem. So we have a 2D environment. An agent starts at the origin. There are 4 regions of high reward, and they're all sort of symmetric. If you learn this, if you apply soft Q learning, and then you get a policy out of that, you will notice that when you sample trajectories under this policy, you will eventually sort of uniformly at random pick one of the directions, and then you will move to that direction and eventually start sampling in that direction, trying to maximize the reward. So the good thing about it is that this framework provides you some sort of principled way to inject noise or uncertainty into the policy, so that the policy tries to be as exploratory as possible, as uncertain as possible, while at the same time trying to maximize the rewards. Right? So it's not just a random walk around the entire map, but it's pretty directed, random walk directed by the reward in a soft manner. And for example, if you look at this picture, if you start at point 2.5, 2.5 here, you will have almost equally like the probability of going either diagonally up or diagonally down. But you can look up more details and more experiments in the papers that I linked on the course webpage. For now, I'll just summarize what we covered so far. So we covered so far policy gradients and Q-learning, and then basically in the last few slides we related them back to the soft version of policy gradients and Q-learning by just taking the max entropy objective that we derived in the last lecture and just swapping it with the standard RL objective. And the benefit of this soft optimality is that, well, first thing, it improves exploration and prevents some sort of collapse of the policy. It turns out that policies oftentimes are easier to fine-tune for more specific tasks. So imagine you had one task and you trained a max entropy policy. Maybe another task would be for the agent to navigate to a slightly different location or maybe accomplish a slightly different thing. So fine-tuning this max entropy policy turns out to be easier. You can look up the details in the papers. Turns out to be more robust. And the nice thing is that it actually collapses to the hard optimality or the standard RL based on the either magnitude of the rewards or if we add the temperature, we can also collapse it to the hard optimality. And finally, the framework is nice also to model suboptimal expert behavior or human behavior. When we ask humans to demonstrate something, and then would like to learn a policy that sort of captures that behavior that human demonstrated, it turns out to be much easier to try to do that within this max entropy framework. But we're not covering this in this class. So you are welcome to look into the inverse RL with the max entropy framework, or refer to Brian Zieber's thesis. All right, are there any questions? Nope. Okay, I guess then that's it for today.